Okay, thank you for introduction. Today I want to say a couple words about the diamond, what is some allotropic form of carbon. But in start, I want to show my group, because without this person, that was not possible to do this a lot of experiment and nice physics, what we do in Krakow. Of course, I want to thanks for our funding. Especially we were working with the Kuna project, what was the TeamNet project, huge collaboration with many groups, especially in the University of Warsaw. Okay, but starting. I say a couple words about the diamonds. Diamonds. Probably everyone heard about the diamonds or brilliant on the rings or something, but why is interesting diamond? Diamond is nice platform. Nice platform. For physics, they have a lot of properties. But for me was very important, the band gap is very huge. So I could put something in this band gap. And transmission is very huge in visible range. For me is very interesting. No, of course, but this is not atomic physics. So what we do with this diamond? So we especially focus on the color centers. The color center is the defect of the diamond, point defect. This is a natural. In the diamond, you spend a lot of measurements with the diamond, I always see some defects. Nature is not very perfect. So what is this defect? This is the point defect. We remove one carbon and include the nitrogen. And around the nitrogen, we looking for the vacancy, so empty place. How we do this? Very simply, in the diamond, natural diamond on synthetic diamond, because we have now techniques when we can produce the diamonds, is always some nitrogen inside. Of course, we can implant it, but if we see something inside, so we need only create the vacancy. How we do this? We irradiate it by proton, electron, something different, what can create our vacancy. Of course, we have nitrogen, we have vacancy. What is the probability they are touched? Very small. So what we do? We annealing, and then vacancy is a little bit moving, attaching the exactly nitrogen, and then we create our color centers. We have three types of color centers, or nitrogen vacancy color centers. Negative, what is much more interested. Neutral, is much more less interesting, but still is promising. And plus, but plus is not shining, so it's not interesting. We focus now in our measurement about not bulk diamonds or big diamonds, but nanodiamonds. Why nanodiamonds? Because it's much easier to attach something to these nanodiamonds. And because this is the carbon, so it's very easy to interact with the cells. So we can attach some fullerenes, some molecules, some drugs, and delivery to the cells. So that's we focus exactly on the nanodiamonds. Of course, the surface effects on this nanodiamonds is very huge problem. We try to calculate what happened when we attach some carboxyl groups or polylysine or something different molecules. But still is not too many papers about this physics. So why people likes this nanodiamonds and color centers? Because we know exactly how looks the electron structure. And what is important in here, the ground state is split by 2.87 gigahertz, so we can control by microwave. So very important for computing science, some quantum technology, for manipulating spins. We can use only the microwave and we can control the population. So this is important. This is very important. And another things, everything is visible in very nice range. So you don't need to some special devices to build the setup and measurement everything, but everything you can do in visible range of spectra. So this setup, this is the setup what built by our student is very simple. This is 1 meter by half meter, and you have everything. You can do all measurement in one small setups. So that's people very likes this nitrogen vacancy. This is some nice picture was showing where people using this nitrogen vacancy color centers. So single photon source, magnetometry, gyrometry, temperature measurements, etc., is a lot of possibility. We now focus much more about the biophysics and fundamental physics, because that gives us our opportunity. So I want to today say about the basic techniques what people using for measurement this nitrogen vacancy color centers. They are called optical detected magnetic resonance. So I said before, the grind state is splitted by 2.87 gigahertz. So, and level of fluorescence is dependent how many population I have here on the ground state. So when I scanning the microwave and going through this resonance between this MS0 and MS plus minus 1, I see drop of the fluorescence. So I can visibly see the resonance. And this is called ODMR spectrum. Why is that important? Because it gives us a lot of information, especially what is applied magnetic field, not only what is the value of magnetic field, but direction of magnetic field. So we have the sensor. And what we can do, we can measure temperature, because the shift of this resonance is dependent on the temperature. What we see here in around the low temperature is almost linear. So we can use this as another sensor. And we have nanodiamonds. We can attach the drug and measure the temperature inside the cells. So this is amazing. So what we do, and this is one of the experiments what we prepared. So here we have the cells. This is our nanodiamond. This is color center. So when we shining the green light, we observe the red fluorescence. And what we see, our cells eating nanodiamonds, so we can observe how looks the transport inside the cells. And probably here someone is cutting the picture, sorry. So there is delivery some drugs, if I could remember. And what we observe, how changing the temperature when we deliver this drugs. So this is very important. But of course, not everything can be attached to the nanodiamond. And one of the problems what we observe, the cells don't like microwave. So okay, sorry, how we can measurement using this optical detector magnetic resonance? We have the microwave, but cells don't like microwave. So what we can do? We need to find the techniques so we don't need the microwave. And we start looking for. So people knows the level of fluorescence is dependent of the value of the magnetic field. In NV centers is very easy, because when you apply it around the 60 millitesla, it's dropping around 50% of the contrast. Okay, that's great and nice, but this is huge magnetic field. This is a very big magnetic field. When you take the permanent magnet, so it's the same magnetic field, so it's very big. So we focus here. What happened here when we very close zero field? So we magnify and scanning the level of fluorescence. And what we observe? Oh, this is some resonance. Very narrow resonance. Is depend, of course, this is the bulk samples, this is the nanodiamonds, is much more broader, but still is visible resonance. And we have some information. We can now measurement the width, contrast, position of this resonance. And we don't need microwave. So this is completely new, open for a lot of measurements. Exactly this paper was published 2 months ago for our group. So what happened here? I don't see the curves. Okay, maybe it's not that much important. This is much more important. So we observe this width and contrast versus the size of nanodiamond and different surface termination. How is depend? Of course, like you see, this is the size is very big. This is not molecule, but we're talking about the 110 nanometers nanometer size of the nanodiamonds. But we see some effects. So we see the strain. So strain inside the lattice is bigger when we go to the smaller nanodiamonds. The width of the resonance is increasing. Okay, this I agree. But what happened with the contrast? What happened with the contrast? Contrast is completely changing, different when we have different size of nanodiamond. So we start thinking, okay, maybe that is something interesting, because when we go to down with the size, the volume surface ratio is completely different. And changing the Fermi level on the surface, because it's completely changing the physics on the between the nitrogen vacancy and termination surface. So we start to explain this, but still we need some simulation to understand some effects. But it is very, very promising for next measurement. So what we do, we start to measurement the temperature with this resonance without the microwave. So we see, is some slope. So we can use this technique to apply it to the cells without the microwave. So we do a lot of measurements with the different sizes and different environments, the different surface termination. Exactly, this result is from last week. So it's completely fresh. And it's a chance to include this technique to the nanodiamond with the termination with the drugs and put to the cells. This is very primarily measurement, so we don't have too much results. And very interesting things what we can do is using the fiber, what was produced by Professor Ryszard Buczyński from Warsaw University, using as an endoscope quantum system when we have the one layer of nanodiamond from the one side and observe in the endoscope mode some magnetic structure. So that is very interesting and promising measurement. So nitrogen vacancy concentration is very interesting. This is a very huge topic. There's a lot of things to do. Like now we focus about this surface termination, so apply some molecules to the surface of nanodiamond and measurement them not only by some different technique, but by optic techniques, and try to simulate it, and that give us a lot of opportunities. So this is everything. Thank you for your attention.
Yeah, thank you very much. So any questions I see there?
Mm-hmm.
Thank you for the talk. You mentioned that luminescence is sensitive to the magnetic field, and I wonder what is the mechanism for this?
Mechanism is because when we look on the electron level structure here, we can focus here. So we have the 0 state and plus minus 1 state. So when we apply the magnetic field, this state is splitting by Zeeman effect. So not all of the population is occupied by now here, both of the states, but is going sometimes to the -1 and +1. This is not in the same weight. So is that is when you're splitting in the huge magnetic field, and the population is a little bit different. So on the ground state, so fluorescence going down. Is okay? No?
Okay.
But the fluorescence should be depend rather on the population of the excited state?
No,
Like
here is about the ground state. This is the difference in the color centers.
Okay.
So this is the difference, because in ground state this is completely different story. We talk about the ground state here.
Okay, next question.
Thanks for the talk. It was very interesting. What is the range of temperatures that you can monitor, and also the resolution that you can get from it?
Okay.
Yes.
Normally we can measure temperature from the 0 Kelvin to 400, because below this temperature is NV is not stable. It's starting the destroy it. What is the resolution? Here is -74 kilohertz per Kelvin. It doesn't mean we can. For real measurement in cells, below 1 Kelvin, we have accuracy.
Okay. Any further questions? Maybe I have the last question.
Mm-hmm.
So you said that the cells are not happy with the microwaves. Yeah. How happy are the cells with these nanodiamonds? Are they surviving long time? Or?
Very happy. This is amazing. I'm not showing this experiment, but we have one nice experiment when we spread nanodiamonds around the cells, and we see, they are eating. nanodiamonds. So maybe this is only something not special. So we spread nanodiamond and latex beads around, and almost 90% of diamond was eating, plastic beads was left.
Okay, and how long these cells survived?
This is 3 days.
Okay.
So this is a very long experiment. That was the problem with how long we need to apply the microwave for how long. That was pulse experiment, not CW, because CW killing very quickly cells.
Okay. There are no further questions. Then thank you very much once again.